So next section of what we're going to look at is all about rates of change, which you may remember we looked at last year. But I suppose the difference with extension 1 rates of change questions and just 2 unit ones is you often need more than one rate to link all the problem together using our, chain rule. So we've seen it used. Implicit differentiation, I suppose, is another way we saw it in context, but using that idea of if I want to find dy dt, I could find dy dx and multiply it by dx to t. So here's a typical sort of question. A spherical balloon is being deflated, so the radius decreases at a constant rate of 10 millimeters per second. Imagine you've got a balloon and it's being decreased, but the actual volume will be changing at a different rate. Because imagine the sound. Okay, so your radius is going down, goes shh, and then what happens right at the end? It goes shh, so as it all rushes out. So we want to know at what rate is it changing when the balloon's 100 millimeters. So let's put together. dv to t is what we want to find. What do we know? We know dr to t is negative 10. It's going down at 10 millimeters per second. dv to t, well, we know dr to t. If I could work out dv dr, we could come up with a formula. So we need a link between volume and radius. Fortunately, we've been told it's a sphere. And we know volume is 4/3 pi r cubed. So dv dr would be 4 pi r squared. So we can now create a formula. Negative 10 times 4 pi r squared, negative 40 pi r squared. We wanted at the time, or when the radius is, where is it? There we are, 100 millimeters. So subbing in, and we get minus 400,000 pi millimeters cubed per second. There we go. Now I'm going to blow a bubble. Now this time, when you think about blowing a bubble, the volume increases at a constant rate. So how is that surface area? Because it'll start out and then go, but actually, as the bubble gets bigger, the surface area increases at a much slower rate. So we want to know ds to t. We've been told dv to t is 70. So I'm going to need a few rates here. So we know dv to t. I can work out ds dr, but I'm also then going to need dv dr to get our final answer. So we worked out dv dr before as 4 pi r squared, so we can use that. ds dr turns out to be 8 pi r. So subbing all that in, I get 140 over r. We want the point when r is 10, so we get 14. So there we go, 14 millimeters squared per second. Here's an HSC question. Oh boy, we're so lucky in nature that these things turn out to be perfect spheres. A spherical raindrop of radius r meters loses water through evaporation at a rate that depends upon its surface area. The rate of change of that volume of the raindrop is given by dv to t is minus 10 to the power of minus 4a. T is in seconds, a is the surface area of the raindrop. Show that dr to t is a constant. Okay, so what is dr to t? That's what we're trying to find. We know dv to t, so if we can find a link yet again between volume and radius, we should be able to come up with a formula. Yep, there it is, hasn't changed. It's still 4 pi r squared. Amazes me actually. Don't you find that fascinating? Differentiate volume with respect to radius, you get surface area. Love that formula. Okay, so dv dr actually, as I said, was equal to the surface area. So I can just call it A. So dr to t, well, we've been told dv to t is minus 10 to the minus 4a. dv dr, well, we want dr to v, turn it upside down, is 1 on a. The a's cancel, leaving me with a constant minus 10 to the power of negative 4. So yes, it's decreasing at a constant rate of 10 to the negative 4 meters per second. Part B. How long does it take for a raindrop of volume 10 to the negative 6 meters cubed to completely evaporate? So dr to t is minus 10 to the negative 4. Volume. We know it's 4/3 pi r cubed. I'm trying to find the radius here so I can substitute into my eventual formula. So 10 to the minus 6 is 4/3 pi r cubed. Rearranging it, there we go. We get a very lovely answer, you'll notice. The radius is the cubed root of 3 times 10 to the power of 6 over 4 pi. You probably guessed that anyway. So I'm going to integrate. Well, because look, we've got an expression that says dr to t. So that's a link between radius and time. It wants to know how long will it take. Well, what's going to be the radius of the raindrop when it's completely evaporated? So I can link time and radius together. I just got to integrate in this case. So I know the integral of dr will equal the integral of dt. But I've got to match the limits up. I'm now saying that when the radius is the cube root of 3 times 10 to the 6 over 4 pi, I know that's initial, so t is 0. When the radius is 0, well, that's what I'm trying to find, so time is t. The actual integrals are very easy. Integrate dr, we get, that's it, the pirate, r. And integrate the t, we'll get t. But subbing in our limits, 0 to the cube root of 3 times 10 to the 6 over 4 pi. There we go. There's our answer. 10 to the power of 4 times the cube root of 3 times 10 to the power of 6 all over 4 pi. Mind you, we probably would convert that to a number if we're telling people. Because as I said, how long does it take? You wouldn't say, oh, that's easy. 10 to the power of 4, cube root of 3 times 10 to the 6 over 4 pi seconds. And that's all. Thank you very much. No. Makes more sense. So 62 seconds that works out to be. So I suppose this is different from last year, because last year when we looked at these rates of change question, we hadn't looked at integration. So now we can go back with some of these rates of change and use integration to help us solve problems. Whoa, hey, woo, slow down. There it is. 7E, 7F.